You might have run into the issue before of having to turn a voltage signal to a current signal. Now, if you haven't, let me give you a real quick use case. Say you have a voltage signal you want to send over a long distance. You'll have a voltage drop across the line, increasing the original amplitude of the signal before it reaches the end destination. Now, the question is, how can we send the signal over the line and account for the voltage drop? If you were to make the signal represented as a current instead, you can send it across the line without having to worry about the voltage drop, as the current throughout the whole cable is the same at any given point. Let's look at a simple example. Here's a circuit powered by 1 volt. To calculate the current, we simply add resistances together in series and use the relationship V equals IR to calculate the current. Now, if you look at the voltage drop across each individual resistor, you can say, irrespective of the resistance, the current flowing through each resistor is the same. Now, representing the signal as a current has the advantage of not needing to worry about the voltage drop across any given component. Now, let's jump into the circuit. In this circuit, we take advantage of one of the key properties of an op-amp. That being at any given time, the voltage of the non-inverting input is equal to the voltage of the inverting input. The op-amp, through its output, will do everything in its power to maintain this relationship. So if we input a 1 volt amplitude signal to the non-inverting terminal of the op-amp, it will drive its output to replicate the voltage across the inverting input. Now we can calculate the current, which is set by choosing the value of the resistor on the return path side. 1 volt amplitude sine wave is now represented by a 1 milliamp sine wave. Here's a simulation of our circuit. We have a 1 volt amplitude sine wave going through the non-inverting input of the op-amp. It then drives a NPN BJT. By driving the transistor, it tries to balance the inverting input to the non-inverting input, so they match. I included some 700 milliohm resistors as well to represent the long cable lengths, and a supply voltage of 5 volts to power the supply side of the circuit. You can now see that as we input our 1 volt amplitude sine wave, we get, well, something that looks sort of what we're going for. There are two issues with this circuit. First issue is, since we're only using a single-sided supply, we can only handle positive swings from the waveform on the input. Thus, the negative half gets cut off when the negative cycle of the sine wave begins. The second issue being, because of the return end of the cable that goes to ground, that additionally has the voltage drop across it as well, which makes the voltage drop across the current resistor slightly smaller. To fix the issue of the negative cycle getting clipped, we can level shift the input sine wave so the negative swing is now offset by a DC voltage that brings it into the positive region. Say, for example, if we level shift at 2 volts, the max most positive swing now goes up to 3 volts, and the negative swing down to 1 volt. To do this, we can use an inverting amplifier with an offset voltage on the non-inverting input. You're probably used to seeing the non-inverting terminal being grounded, which gets rid of the DC offset and just leaves the normal equation. This now introduces a DC offset in our waveform, but it's something we can later filter out as we only care about the AC signal swings, which will oscillate now around 2 volts. Now, having added the offset voltage, we can see the output from our inverting amplifier. We have a DC shifted sine wave that oscillates around 2 volts and is 2 volts peak to peak. Looking at the inverting terminal, we can see that the output doesn't exactly match the input though. This is because of that 700 milliohm return cable length, which adds an additional resistance in line, which drops the voltage slightly across the current set resistor. If we look at the difference between the input signal and the voltage drop from the return cable, we can compare to the original signal and then have an op-amp do a corresponding correction. Remember that an op-amp will always try to balance its inputs so that when it sees a 2.998 volt peak compared to our input peak, which reaches 3 volts, it will drive its output to accommodate it by having a higher output voltage to overcome the voltage drop. To take the difference between our input voltage and offset voltage from the return wire, we use a difference amplifier, which we then feed back into an op-amp, where it compares it to our original signal, and then makes the corresponding adjustment to the output to drive the signal slightly higher so it can make the adjustment for the offset voltage. If we look at the output now, on the inverting terminal on the output, We can see that it exactly matches the input signal we have, thus showing that our op amp makes the corresponding output for the voltage drop across the resistance of the wire. We can now change the resistance of the wire so it can be practically anything, and it will make the corresponding adjustment so it will always match the input voltage.